Good morning, and thanks for the invitation. It's a pleasure to be here in a different university with different perspectives and different backgrounds, talking about machine learning and artificial intelligence. In this talk, I'm going to summarize a little bit 2 or 3 words that we have been developing in the recent years. In fact, one of the papers in this talk is going to be presented in 2 weeks, so it's quite fresh recent work. And this is going to be the
es que está encendido.
Sí. Ahora.
Es en mi mano.
So this is going to be the outline of my talk. First, I'm going to introduce the general perspective of the presentation. Then I will talk a little bit about the learning systems I'm going to compare in this talk. Then I will present the framework or the theoretical background of the approach of machine teaching. We have developed a new approach or paradigm of machine teaching, and then I will summarize a little bit the theoretical framework of this new approach. We have implemented this theoretical framework using a language that is called 53, will be the 5th one. Finally, I will present some experimental results comparing this learning system, and this will be set in point 6 and 7. I will finish my presentation with the conclusions. So, recently, or since several years ago, we have seen how machine learning and artificial intelligence is getting more important thanks to the capacity of learning from data. Okay, each different system, in each of these different systems, you can find different prior or different bias according in which the way they are developed. For instance, we can see that some systems are able to learn from strengthening patterns, like this one, twinkle, twinkle, little star, and others are able to learn from interesting patterns, like on, off, and then you generalize to off. So we believe that it's important to understand how these different learning systems are able to learn in order to get an effective and reliable interaction between humans and learning systems. In this context, we can see very recently, maybe 2 or 3 years ago, very powerful language models that has been trained over massive natural language corpora, and they are really good, first, at exploiting the expecting patterns for away from humans, and also, the stronger version, the latest versions, can also identify some intrinsic patterns in the prompts. And they are considered as pixel learners. Okay. So the main goal of my presentation is to study the learning priors of different machine learning systems, and we will compare these priors with respect to the way the humans learn. Okay? This is like the main goal of this presentation. And if we divide this main goal into different questions, we want to address questions like how elaborate can these abstractions be, or can they even have an algorithm not used, or what is the minimal set of examples for a learning function. Okay, and at the end we want to find if there are priors inside of these pre-trained language models incarnate for future learning to work. And the key idea of this comparison is based on a quite new framework that is called machine teaching. Machine teaching can be seen like an inverse problem of machine learning setting. So in machine teaching, the goal is to find the minimal set of examples in which we are able to teach a concept, to teach a problem. Okay, so it's an area that looks for the optimal examples that a teacher should use to make a learner capture a concept. Given a concept, we want to find a witness set that allows a learner to uniquely identify this concept. And if we are using rich representation language, similar to human language, there are several advantages. For instance, we are able to find effective teaching with few examples. And we also have found that the example set is usually shorter than the algorithmic expression of the concept itself. So this is like the key concept of the selection of the example. So,
one question. Since the slide before,
yeah.
Is this concept related to something? There is something in computational learning theory about a concept about the probability of approximately correct, which is actually giving you the minimum amount of examples that an algorithm needs in order to learn a concept. Is this related to that?
Yeah, it's quite related. In fact, there are some theoretical results about this path learning and machine teaching. Okay. And a concept that is called the teaching concept, the teaching dimension. And okay. There are some, it's quite related. Good point. So the goals of the talk is we're going to introduce a practical machine learning framework based on a fully complex language. And from this framework, we are going to select a set of examples in which we are using to explore the number of the lengths of example models needed to learn from prompts. We will also analyze whether a sample set probably is acquired or skilled as a result of the training large language models. And we will compare also other artificial systems with humans and with this language. This is like the generic goals of my talk. So let's talk about the concept learning systems. As I have thought, our objective is to compare the learning mechanism of artificial intelligence with respect to humans. In artificial intelligence, the area that is focused in learning is called machine learning, and is defined as the study of computer algorithms that can improve automatically through experience and by the use of data. And this is done by a technique that is called inductive inference, in which we want to infer knowledge from data. Okay. However, many or most of the well-known methods are based on huge amount of data. For instance, the popular network networks or deep learning. We need a lot of data to train good models in this perspective. Since we want to compare learning systems with humans, we cannot give thousands of examples to a human. So we need to concentrate on systems that are able to learn from few examples. Okay? So we can not use network networks or deep learning directly. We need to employ other techniques. Talking with about few examples, there is a technique that is called inductive programming that is like the most used paradigm when we want to use, when we only have few examples to learn from. This inductive programming is an interdisciplinary domain of artificial intelligence and cognitive science. And the goal of this domain is to study the automatic synthesis of computer programs. So it's a quite old technique, mainly developed in order to build programs automatically from few examples. This inductive inference makes generalization from observation, from examples, from evidence, by identifying general patterns in the data. Usually, inductive programming has two different incarnations. One based on logic programming, that is called inductive logic programming. Another one based on functional programming. So two different paradigms of programming. So this is called inductive logic programming or inductive functional programming. And probably the most successful technique or implementation or application of this technique is programming by example, in which we give some very basic examples of the function we want to learn, and the system is able to develop a program that is able to cover that example. Do you know what tool that is called flash fill in Excel? In which you put some examples and the Excel is able to develop the function that you want to use. Don't you know this? It's like the most famous. It's quite useful for the people that they don't know how to use Excel, because most of the people using Excel, they are not able to write a function. So, and this technique is able to develop automatically function like you want to extract the first name of when you have name and surname, something like that, or you have to translate capital letter to not capital letter, something like that. Okay, so this is probably the most well-known application of programming by example. As I told you, there are two most well-known versions of inductive programming. The first one is a technique called inductive logic programming that is based on a paradigm called logic programming. Logic programming was or is a technique that was created 40 years ago, in which probably do you know Prolog language? It's a quite common language used in artificial intelligence, in which we are able to express knowledge in terms of logic, of first order logic. So the idea of inductive logic programming is to use a uniform representation for examples, background knowledge. We refer to the functions we already know, to well-established knowledge, and hypotheses. So the idea is to have some positive examples, negative examples, the knowledge we already know, background knowledge, and the idea is to extract a hypothesis in a form of a logic programming. So this is more or less the idea of this inductive logic programming. Probably in the most famous systems of inductive logic programming, there are Prolog and these are like the conditions required to satisfy a framework of inductive logic programming.
Can you give an example?
Yeah, I'm going to put this. This is an example.
Yeah, perfect.
So this is like the classical example of inductive logic programming, in which we have a set of facts about a family, and using inductive logic programming technique, we are able to learn relationship between these facts using this kind of representation. Okay, this has been widely used in, for instance, for chemistry and biological science, this kind of things, because you can express, for instance, genes or other complex relationships with these techniques. So related to inductive programming, we found also inductive functional programming that is based on functional programming. That is different paradigm in programming, but it's quite related. Okay, and then the good things of these two learning paradigms is they are able to learn from very few examples. So it's the big difference with respect to decision trees or supervector machines or neural networks. And then recently we have found a new application from language models. Language models are models from natural language processing, and the main goal is to estimate the probability of a given sequence of characters following another sequence. It's the typical thing when you are using Google and you write Valencia is, and then Google suggests you some sentences after that. This is like the origin of language models, these kinds of certainties. However, in the last years, motivated by OpenAI or Google, the companies, they have invested huge amounts of money in order to develop really strong language models that have been trained with terabytes of information, of textual information from it. And they have developed systems like BERT, have you ever heard about this? They are quite big, right? Okay, so these are language models that have told you they are based on actually training huge amount of data, and they are based in systems that are called transformers. And well, these language models have been quite surprising or attractive because they have shown capacity of first exploiting existing patterns borrowed from humans. They have been trained from text generated by humans. This is the thing we see when we are using Google, that Google is able to complete quite correctly your text when you are writing down a sentence. But however, these strong versions can also identify some interesting patterns in the prompts. I will explain a little bit think about prompts. And in this way, there are in the 2 or 3 last years, there are papers when the authors have demonstrated that these kind of models can solve, for instance, mathematical problems, or question answering, or language understanding, even code generation. Recently, in the last months, there's a version of GPT-3 specially developed for generating code that is impressive. I don't know, it's called Codex, and there is a version that is called GPT GitHub Pilot, because there is like an agreement between GitHub and OpenAI in order to develop this tool. And I don't know if you have seen some videos. You write a specification of the program you want to write, and the system automatically generates the function. It's amazing. And also, this is something in which we have a paper. We can use language models in order to specify or generate a simple function that helps you to do some data running. Data running refers to data cleaning, data transformation. Okay. So if you don't have experience in language models, you can get a little bit surprised how these kind of models are able to do these kind of things. And the key point of these language models are prompts. Prompts is the only input that these language models receive. So you need to train a little bit. How do you want to employ the language model? So here, these are examples copied for the specification of OpenAI GPT-3. So I have selected 2 or 3 in order to show you how it works. So if you want to use, for instance, GPT-3 as a sentiment classifier, you need to put some basic examples in the prompt, and then it is the question you make to the language model. And then the language model will answer you here, theoretically, if it works well, positive or negative. Okay, should be positive. Okay? And the good thing is that it's working very well. So here is a different problem in which you write down some sentences with cities and you want to obtain the codes of the airport. And even it can work with emojis. This is like an example in which you write some titles of movies, and the language model is able to generate a sequence of emojis representations. Okay, so it's amazing the power of the capacity of learning of these language models. Then, as I told you, our idea is to compare how these different language learning systems learn in comparison with humans. And we want to use few examples because we want to compare this system with humans, and we cannot put 1,000 of examples with humans. We need to use very few examples if we don't want to get tired of the human discussion. How do we generate examples? And here is where we are going to use machine teaching. I I told you before, machine teaching is a technique that the idea is given a concept, for instance, reverse, we want to use this machine teaching system in order to find a set of examples in which we can teach that concept to a learner. Okay, so this is an area that looks for the optimal examples that a teacher should use to make a learner to come to the concept. Theoretically or traditionally, machine teaching has been developed using the concept of teaching dimension related to this fact theory, and you will see the number. This teaching the dimension has been defined as the minimum cardinality of a wideness set for the concept. In maximum, the problem of this teaching dimension is sometimes the maximum will usually be unbounded, and even if we adopt a preference-based order on concept, the maximum is still unbounded and incomputable. Additionally, this concept, this definition of teaching dimension has several problems. For some contexts, can be taught with very few examples, but those examples could be really learned. So even though we have very few examples, they are almost infinite. So we ask if we want to apply teaching dimension, machine teaching dimension is not very useful. We need to develop something new, and we developed or we're thinking about the concept of size. The goal of this new framework will be: can we define a new teaching method that is more personally related to how is to teach concept, to teach a concept? But here, I went on a little bit of the notation we are going to use in this framework. This part is a bit theoretical. We are going to consider a sample space of concepts, an infinite concept class C, consisting of concepts that are a set of X. For any concept, the teacher must find a small witness set of positive examples. An example set, or it's a set of pairs in which we have input and output. And we say that a concept satisfies a witness set or an example set, and we denote by this symbol if for all the pairs in the set, all the concepts satisfy this one example. Okay, so using this notation, the thing we do is develop a new definition that is called teaching site. The teaching site of a concept could be defined as follows. We employ a function, a delta function, that measures in number of bytes the size of the witness set. In that order, we want to find the minimal witness set measured in number of bytes using this delta function, in which we can teach a concept to a learner. Okay, so the minimal set is known as a witness set for the concept C, and ES depends on what a concept and a learner. For our framework, we need to set an order in the number of programs. We are going to call the symbol with to specify the order of programs. And in this order, we want to use the size of the program. First, the size of the program, because we want to have the program with fewer expecting receiving longer program. And we also establish the lexicographic order for programs, having an order in the number of programs. Given that we are going to have problems with compatibility, we are going to establish this function or this definition. We say that program is compatible with example set, denoted with this. If for parts of input output of the set of programs, the program P on input I will within a certain time steps have a specific behavior. So we limit. We limit the running time because some programs will will run infinitely. We need to establish a limit in time in order to compute the compatibility of this of programs. Okay.
Yeah. So I was wondering if you allow for not to learn the concept exactly, but you allow for a approximation of the concept.
No. In this framework, we don't allow approximation.
You require to learn the concept exactly.
Yeah, but it's something we are working on that. We are like extending this framework, considering probabilistic approximation. This kind of thing. Always something we are considering.
I was wondering what.
A good point. In fact, this is one of the main restriction of this framework.
Great.
Okay, so considering this as compatibility, we developed a new definition that is here teaching size, in which we are able to establish this machine teaching framework. And with this framework, we are able, or we want to write what we call teaching book. What is the teaching book? The teaching book is a list of pairs in the form of programs and witness set, in which for each program we find the smallest program compatible with the smallest witness for that. So sorry, I have written that. We have a program P, and W refers to the minimal witness set that in which we are able to learn that program. Okay, so the teacher is the one that fills each teaching book, called it because it's based on this in this version of the teaching sites. The teacher must generate the example sets in the teaching sites, and for each example set, we write programs of increasing length until finding the first one with the correct behavior. So in the teaching book, the learner, the thing he needs to do is given a witness set, the learner wants to find this smallest program with the compatibility. So we give the teaching book to the learner in that way. If the teaching is giving a set W, the learner is able automatically to find the corresponding program. We have found, we have some results, theoretical results about the compatibility of this teaching book, and we are able to show that the learner is computable and the teacher is computable. And how do we generate this teaching book? Good force. So since we have an order in programs and we have an order in witness sets, we try all witness sets with no contradictory pairs, but allowing the empty output in an order of no decreasing encoding size. We run the learning algorithm on W to find the program P, and with this test if the program P found by the learner on this witness set is already in the teaching. And if it is not, we are there. So with this good algorithm, we are able to find a teaching book in which we have a program and the minimal witness set corresponding. So this was like the theoretical framework. So the thing we do is to put in practice. How did we do? So the thing we did is to employ a language program that is called P3. Probably you don't know that, but if I say brain fact, have you ever? So this P3 is based on brain fact, and it's a really simple language program that I will explain a little bit after the slide. And so as learning prior, we take the preference order in some program size and this complexity function, and we are going to use an encoding that is called Elias delta coding in order to compute the size of the number of bits of the witnesses. This Elias delta code is an old definition encoding scheme that is able to compute the number of bytes, the size of the witnesses, even if there are more than just one pair. So what is P3? P3, as I told you, is a variant of brain fact. It has only 7 instructions. We have these operations that are used to move like a pointer. We are going to use like an array in memory, and we have like a pointer, and these 2 operators are useful to move this pointer. Then we have two instructions that are used to increase or decrease the value of the pointer. We have this instruction O, this output, in order to print the value of the pointer, and loops are implemented by brackets. Okay? So the thing we put inside the brackets is like a loop, and the loop is running until the pointer is finding this point value. And we have only three symbols, 0, 1, and the pointer in order to finish the.
So every point for the last is very analogous for me to a Turing machine.
Yes, it has some similarity.
Yeah, it's just that the Turing machine, the last point is, I mean, the loop is hard code, or I don't know if it is like a modern way of encoding sort of a Turing machine.
Yeah. Exactly.
Okay.
It's Turing complex. So this
No.
is, so here you can see some examples. So for instance, this program is like the identity program. It gets an input array and it puts it just outputs the end. Okay. If you see how it works, you have a loop where in which you first you print the character and then move to the right. And then you get into a loop until you arrive to the left, arrive to the last symbol in the input string, and then you stop. Okay, here you have reverse, to be reverse, to 0, 0, to 0, 1. So these are practical examples of concepts and the example set in which we were able to teach the learning this concept. Okay, so this is
For the reverse, this is the minimum amount of example you have to give an interpreter.
yeah, exactly.
Is a unique set, or there could be other two examples that are?
Well, there could be other examples in which you can teach that concept, but this is the minimal. In measuring this witness set, it's an example set with this delta code. So because we are only interested in the minimal one. Well, so the thing we do is we develop two versions of the teaching book, one with just one pair, another one with more than two pairs, one pair, sorry. And here there are some examples in which, for instance, given this example, the learner is able to find the entry or with that example, the learner is able to find the. So, and here you have results for in number of, when we compare the number of bits, the size of the program with respect to the size of the evidence in order to teach that program. So we can see some important clusters and really simple programs in that area, which we are able to teach this simple concept with few examples. And as expected, we find like a correlation inside of the concept and in the video.
For all these concepts, the minimum program is always unique. The minimum, witness set is always unique.
Yeah, because we have a order of witness sets in size, and we have a lexical order.
So it's always only one answer.
Exactly. You can find maybe witnesses with the same number of bits, but given that we have a lexical order in the witness set, we select everything. But it's true that in this aspect is something one of the reviewers comment that is like an arbitrary choice, because we select 0 before 1, but not why. So at the end, it's something you need to put in practice if you want to define a problem. Otherwise,
I don't know. I would assume if you want to teach some simple concept, the witness set could be very simple as well. Very simple, but there could also be more variety of moves. Like the witness set could be different. Like there are many ways of teaching the same concept with a similar size. Maybe
Yeah, you're right. Maybe you are able to find other window sets with same size, but in our framework we have this.
I guess it's related. The diversity of which you can replace the same concept will also be related to how simple it is. But in your framework, it will appear because it's unique.
Exactly. So this is more experiment in this case with a teaching book with only one pair, and there is something quite interesting. Is this plot? This line is the diagonal, and here we show that there are many concepts, most of them, in which we find that it's cheaper to send the winnet set than to send the program. So if we compare the number of bytes of winnet sets with respect to the program length, we see that there are many cases in which it's simpler or it's cheaper to teach to send the winnet set instead of the program. So some observation of this framework, we have been able to demonstrate the computability of a practical teaching theoretical setting, in this case using P3. We have found that teaching books have high number of high diversity programs. We have limited the diversity with one or more pairs, and I have told you it's common to find winnet sets that are smaller than the programs that they identify, according to Elias Delta Code. And which applications could have this machine teaching framework? Well, we think we are going to have some application of machine teaching in human-computer interaction. It's really important to define, to select really representative examples if we want to interact with humans, because we don't want to get to over causal like that stress, because given a lot of data, we need to select the key examples to teach concepts. This could be really useful for education, for AI, or coding. Okay, so this could be also very useful when we have some interaction with artificial agents, when we can benefit from a better understanding of how humans respond. So now we have like the application framework in which we are able to, given a concept, generate the minimal set in which we are able to teach this concept. And this is like the base in which we are going to compare language learning systems. So considering this teaching book, we are going to select 8 different concepts, and we are going to define 4 levels of complexity. Very low complexity, high complexity, and very high complexity. And how do we define this complexity? According to the numbers of operators we find in this program. Okay. Then we generate 3 batches of training data. The minimal winnet sets we select according to this teaching book, and then we generate extra data in order to give more information about the concept. The first batch consisting of 2 extra samples, and the second batch with the extra samples. This is like, this could be the training set. And for the test examples, we generate 5 examples in which we are able to test if the learner has been able to understand correctly the concept. So this is an example of 2 concepts we are going to employ to compare systems. We have the program, but at the end, this is not really important because we are only going to employ examples. So humans or learning systems, they don't care about how the internal representation of this concept. In fact, the useful thing is the description of the concept. For instance, this is why French concept is really easy. It's just to print the first character of the string. And here is we have the minimal winnet set. the first extra batch with 2 examples, the second extra batch with 3 more examples, and the test examples.
Okay, I don't understand why
Sorry, repeat it.
No, I just don't understand why this the witness set.
Yeah, because we have run our machine teaching framework, and we have found that we are able to teach this concept with this set. So it's the way this machine teaching what is doing. Okay. According to this implementation of machine teaching, we are able to assume that this is the minimal limit set in which this P3 is able to learn. Okay, according to this simplicity, because we are based on size. You understand?
Yeah.
Okay, so these are the 3 batches from the learning and the test.
I guess in that example, it's just difficult to imagine how human will get that this is the rule.
Yeah, exactly.
It's just, I guess that
Yeah. This is really difficult to learn. But not only for humans, also for logic programming or other.
The point is that if the cell contains the period, then you don't print it out.
No.
Otherwise, it's print one.
Yeah, so.
If it starts with the one, then when you do the plot, it goes to the period, and then the period is not print anything you must show.
Yeah. Okay, so this is really simple concept, and it's more complex concept according to this classification. So, well, what are we going to compare? We are going to compare humans. We had 50 students that were really helpful. With the thing we do is we did a web form in which we sent out to our students in data science degree, and some of them answered. We have these 30 human participants between 18 and 24. Then we have Magic Haskell. Magic Haskell is a IT system based on functional programming. It's really powerful. It's a very nice system. We have Rez, that is a last generation system on inductive programming. And then we are going to compare 2 different kinds of language models. GPT-2, that is like the previous version of the GPT family. Here we have 2 kinds of implementations. Well, this model was trained with almost 800 million of parameters. And here we have 2 different versions, GPT-2-Ens, that is the most frequent result, and GPT-2-S. And the thing we do is do average results. Because in some cases, this GPT is not deterministic. That's the reason we need to run it several times. And then we have GPT-3, it's the last version. I think this is expected to have the GPT-4 in few days or few months. And then we compare 4 different versions, Ada, Bagage, Fuji, and DaVinci. The difference between this version is the number of parameters. So theoretically, the most powerful is DaVinci. I think they only the energy they employ to train this version, it was like $12 billion, only the energy. So there's like a brute force algorithm in order to train these language models. And we have also different versions, deterministic and like this GPT. So prompts. As I told you before, it's so important to define correctly prompts. We were exploring different kinds of prompts. At the end, the most successful prompts were these 2. The first one is for GPT-2, and the second one is the GPT-3. The difference is if we have the inputs in different lines or not. And if they are quite simple, we say this is the input, output, input, which is the output. Okay. So, and these are the results. Here we have the results with in which we compare different versions of 53. And the results here, for instance, are quite spectacular because we see that when we give more evidence to the learner, the accuracy increases. And we also see that the most powerful versions of GPT-3, GPT-3 Da Vinci, is the best one. So in some sense, we are able to find what we want to find. If we compare the results with respect to difficulty, again, we find something similar. The only exception is the very complex concept in which we have quite an expectable high accuracy in comparison with the rest. But if you see the level of accuracy, you can see that, for instance, only with the witness set, even if it is not able to find a lot. So not only humans have a problem with that. Okay, and this is like the comparison of humans with the other learning systems, in which we see that the most successful system is 53, followed by Luis, but ILP, and then followed by humans. We find again a quite expectable behavior in which, when we give more evidence, the learners are able to learn better. And here again, we have like this very strange behavior with a very complex system. Okay.
It's because it comes from the visual for
The humans are the it's quite small. It's blue. Blue.
Like,
The right.
yeah,
Yeah, they did work quite well.
students at the university.
Yeah, but you have in the problems. The problems are
And not
this. You don't need to be like a computer scientist because it's just input and output. Our patterns. Okay, so a little bit motivated by this strange behavior, the thing we did is to run experiments with more concepts, with 300 concepts. But we cannot send 300 concepts to humans, unfortunately. So we did these experiments to 53, and we got something that is more reasonable or more expectable. That here is the complexity of concepts for the correlation with accuracy. Simple concepts obtain better results that are very complex. So we also ask humans about not only to complete the questions, also to try to explain the patterns. And here we have results about the correctness of the explanation according to the complexity of concepts and the size of explanations. Since they were not able to answer very complex concepts, here most of the humans didn't answer, or they gave incorrect explanation. However, for the simple concept, they were able to provide correct explanation in many cases. And finally, we compared by means of disagreement metrics how similar are the answers of these different learning systems. And we found that, for instance, humans, well, we found quite expectable things like language model correlates a lot between them. But if we compare humans, we can see that the most similar system here was ILP, quite kind of expectable, and in this case, a similar result we find if we are using this big coefficient. So, as the conclusions of my talk, first we have developed a new machine teaching framework based on the concept of size. And we have implemented this machine teaching framework using P3. And this allows us to have a teaching book in which we have pairs of concepts and pairs that allow us to have some practical application. And we have employed this machine teaching framework in order to compare the performance and the behavior of different learning systems. In this case, language models, inductive programming systems, and humans. Okay, we have studied different things like different complexity of concepts, different size of evidence, and the agreement in behavior. And we have our main finding is that large language models are quite good at computing low complexity patterns and depends on specific priors, distilling some kind of occurrence razor. Do you know this concept of however, when we consider complex concepts, which are the concepts that are in low loops, language models are not able to get in many of these concepts. So the models in the future might not be able to solve complex algorithm concepts. And the distillation, in the sense, is limited to sequential algorithm patterns. Limitation of our approach. Well, Martin Haskell and Lewis follow simplistic priors, but depend highly on background knowledge. This is especially the case for ILP. This limits because not only tests, not powerful language models, but other AI approaches. So we have the limitation on humans. We cannot use a lot of concepts with humans. So it was a strong limitation in our work. We were able to have only 8 concepts. And we want to keep on performing studies comparing humans and web models. And also, it's related to your question. This setting assumes perfect alignment and identification. We were able to use the machine teaching setting to get the minimal witness set. But for instance, the extra training sets were generated algorithmically without the matching system. In that way, we think that developing a framework probabilistic, we will give more evidence about the competence of the identification. And finally, as the takeaway sentence, we believe that these machine teaching frameworks or techniques can be employed to extract important insights about learning systems or language models can do, and the number or set of examples they give. As I told you, this presentation is like the summary of 3 different papers. The first one is teaching science, computable features and learners for universal languages. This was developed by Jan Tele, is there, my colleague Jose Hernandez Orayo, and myself, and this was presented in the Machine Learning Journal 2 years ago. And this is like the theoretical development of the teaching side. Then we employ this framework in order to extract explanations of concepts in this chapter with my colleague Jose. And finally, the part in which we compare learning systems has been recently published in this first paper, Think Big, Teach Small, 2 language models with open razor. That's going to be presented in this conference in 2 weeks. And that's all. Thank you.